Hi, welcome to Dissolve Chemistry. Let us continue our discussion on this thermodynamics. In the previous video, we have discussed regarding enthalpy of atomization and we stopped there only. So let us continue with our discussion on next enthalpy, that is ionization enthalpy. Or we can call it as enthalpy of ionization, we can say. Okay. Delta IEH represent like this. Okay. So now what do you mean by this ionization? Removal of loosely held electron from the valence shell of an atom or ion. We call it as what? Ionization. Okay. And this ionization, as we know that it requires an energy to remove that electron. And this removal of electron usually it is not from an atom which is bounded in the crystal lattice. It should be a gaseous atom. So now let us define this ionization enthalpy means. The change in enthalpy when an from 1 mole of gaseous atom or ion is called ionization enthalpy. So you may be worrying about that why it is used as ions, because we are going to remove an electron from an atom. After removal of that only it converts into ion. Of course, in many cases what we see is removal of the second electron we do, removal of the third electron we do. Hence I have used the term included, that is ion. Okay. So the atom should be gaseous. From that we are going to remove the electron. Say for example you take sodium gas. Okay, sodium metal vaporized, and from that, so if we remove the electron, or that is nothing but what? After removal of the electron, what it turns out to be? Gaseous ion. So therefore we call it as ionization. And whatever the enthalpy we need, and that enthalpy is called ionization enthalpy. Okay. Usually ionization enthalpy all are endothermic in nature because removal requires energy. Okay. So now this is what we call it as ionization enthalpy. Now suppose if you want to remove the second electron or third electron from an atom, then what it is said to be? So now suppose for example it's a monovalent. Of course it's a first group element, it will give only one electron. Okay, generally. So we can remove the second electron, but here removal of the second electron is very difficult because it is having only noble gas core or stable electronic configuration sodium ion is having. Okay. So for example, you can consider magnesium, you take second group element. Okay. So there removal of first electron. Okay. First electron we call it as what? IE1, ionization enthalpy 1. So then you will get Mg plus 1 plus 1 electron you will get, and that we call it as what? IE1 H. Okay. So then next is, so now removal of the second electron, right? So removal of the second electron, now it involves what? Removal from the ion, not from the gaseous atom. This as what? IE2. What is the meaning of this? Ionization enthalpy 2. Second ionization enthalpy we call that. Mg plus 2 plus 1 electron. So therefore delta IE2H. And always remember, so this IE1 and IE2 will be always what? Different values, first thing. And second one is always IE2 is greater than IE1. Ionization enthalpy 1. So now, what is the reason for that? Because removal of the second or third electron involves a removal from ions, not from atoms. Okay, so that's why it is high. So now overall, if you want to remove 2 electrons, then we call it as what? We are going to add total ionization enthalpy is equal to IE1 plus IE2. So that is how we are going to calculate ionization enthalpy. So whenever it involves 2 or more electrons when we remove, then sum of all the ionization enthalpies is nothing but what? Total ionization enthalpy of removing number of electrons. Okay. So that is all about ionization enthalpy. Bond dissociation enthalpy. So bond dissociation enthalpy means what? If it is a diatomic molecule, okay, it involves breaking of one bond which is present between them. Say for example, you take hydrogen molecule. Now we are dissociating to give 2 hydrogen atoms, and here we call it as what? Enthalpy of atomization and bond enthalpy. Both are one and the same because only one bond is there between the two. So therefore bond dissociation enthalpy and enthalpy of atomization is exactly same. So now suppose if you consider a molecule like methane, okay, so how we will write the structure of this, okay, methane molecule. Now we will be finding 4 CH bonds are there, right? And all these 4 CH bonds. So now you want to break that one completely. If you break, so that we call it as what? Enthalpy. So all the 4 bonds were when broken to give carbon plus 4 hydrogen atoms. Okay. So then that enthalpy we will give as 1667 kilojoules per mole amount of energy is required. That is plus sign we will indicate. Right. So now what it is? Complete dissociation of all the 4 bonds, and we need this much amount of energy. Now how to define this bond dissociation enthalpy? You should remember that each CH bond breakage in methane molecule involves different amount of energy. Okay, slightly it is going to differ from one another. So that we will see first. Okay, CH3 gas. This is also gas plus H. You will get first bond we have broken. So then the enthalpy will be what? Is equal to 427 kilojoules. Okay. Similarly, so now the breakage of the next bond will be either from the radical. Okay, if it would have cleaved homolytically, so then you will be getting radical. So removal of the secondary electron involves from the radical, for it is like this we will write. So therefore CS2, okay, so we will write like this plus H, and we will be having delta H is equal to 439 kilojoules. Okay, then next is, you make this 1660. Then the next bond is CH plus H, we will be getting delta H is equal to 452 kilojoules. That last bond cleaved will be CH to give C plus H. So that delta H is equal to 347 kilojoules. Okay. So now the total energy required to break all the 4 bonds is 1665 kilojoules per mole. But when you take individual bonds, it is going to vary. Okay. Now how to say that what is the bond enthalpy or bond dissociation enthalpy of CH bond? Then that we will take it as what? Average energy required to break a bond, okay, in a what? Multi-atomic molecule if you consider. So then we will take average energy. Okay. So now we will take the average of this overall when you add all these energies, 4 energies. Okay. So then what we will get? 1665 is the total energy. So therefore, average, how it becomes? Just you divide that by 4. See here, delta H total is equal to 1665 kilojoules per mole we have for all the 4 bonds to break. But per CH bond, how much energy? Average energy we call, not a individual energy. So then what you have to do, total CH, how many bonds will be there in a methane molecule? So it will be 4 bonds. So therefore you have to divide this by 4. Okay. So then we will 416 kilojoules per mole of the bond. Bond dissociation enthalpy of a CH bond. CH bond corresponds to 416 kilojoules per mole. So I think now we have understood what do you mean by bond dissociation enthalpy. If it is an multi-atomic molecule, in that case the individual bond breaking energy will be differing from one another, but we are considering it as average bond energy. So therefore what you have to do, overall to break all those bonds, how much energy is liberated divided by the number of bonds if we do, so then we will get average energy, and that average energy is called bond dissociation enthalpy of a particular bond. Okay, so now let us define this. The average enthalpy change when one mole of a particular bond is broken completely, is called bond dissociation enthalpy, or bond enthalpy we call. And we must remember bond enthalpy. Of course, the amount of energy required to break the bond will be always the amount of energy liberated during the formation of that bond. Okay, so we can say in that words also. Okay, amount of energy liberated during the formation of that particular bond is also called as bond enthalpy or bond dissociation enthalpy. Okay, so we'll do problems on this in upcoming videos. So we will switch on to the next important, that is lattice enthalpy. Lattice enthalpy, usually it is represented as U. Okay, so we'll define this. What do you mean by lattice enthalpy? See how these ionic compounds are formed. The ionic compounds are formed by the electrostatic force of attraction between the oppositely charged ions. So they will come and accumulate to form a particular crystal structures. And during their formation, when the cation and anion, n number of cations, say for example Na plus Cl minus, gaseous ions by electrostatic force of attraction, when they come closer to one another. Okay, so when they come and form the crystal, during which what happens, a lot of energy is being liberated, and that energy, okay, we call it as what? Lattice enthalpy. And the same amount of the energy when we supply to the crystal, so then what happens, we can break that crystal to give the gaseous atoms. Okay, the same thing what we can call, either during the formation whatever the amount of energy is being liberated, so that we call it as lattice enthalpy, or the amount of energy required to break that crystal into gaseous atoms, so that gaseous ion, so that we call it as what? Lattice enthalpy. Okay, so let us define that. The lattice enthalpy is defined as the change in enthalpy when 1 mole of ionic crystal change in enthalpy when 1 mole of ionic crystal is completely broken into gaseous ions is called lattice enthalpy. Or in other words, we can define in another way. So the change in enthalpy when 1 mole of ionic solid formed by the combination of its gaseous ions, that also referred as what? Lattice enthalpy. So let us write this. Now, this lattice enthalpy, it is very difficult to determine directly experimentally. So therefore, we can determine by using Born Haber cycle. Okay, this Born Haber cycle was designed based on the Husse's law. Okay, where Husse's law of constant heat summation that we have discussed in our previous video. So what it implies or what means is that the overall change in enthalpy of a reaction, so either you bring it in single step or in multiple step, it is always same or constant, we call. Okay. So now, say for example, we will design this Born Haber cycle for lattice enthalpy to calculate lattice enthalpy. Okay. So let us take one example and we will illustrate that. See here, next you write heading Born Haber cycle. Here, not only by using Born Haber cycle, we can calculate lattice enthalpy. You can calculate any enthalpy which is unknown and rest are known. Okay. So we will see this Born Haber cycle. See, for example, sodium solid. Okay. So combines with half Cl2 gas to give sodium chloride crystal. Okay, so this we call it as what? These two are elements combining to form the compound, so therefore we call it as what? Enthalpy of formation. Okay, so delta H of formation, so that we call, isn't it? Right. So now this we can do that change in energy we can get, or indirectly how we can get that one. Let us see that one in multiple steps. So now to bring this combination, already we have defined lattice enthalpy means combination of the gaseous ions. Gaseous ions, to get what you have to do, you have to sodium solid, so that has to be converted into gas. So then it has to be ionized. Okay, then it will form sodium cation. Then chlorine molecule is there, you have to dissociate it. Then it will accept the electron and form anion. And after that, they are going to combine and form the NaCl solid. So we will see step by step what it is going to happen. So now, Na solid, okay, we are converting that into, we will call sublimation energy or sublimation enthalpy. So then what happens? Na gas we are going to convert. And sublimation enthalpy means amount of energy required to break 1 mole of solid into what? Gaseous atoms. Now after that, what you have to do? You have to convert that into ions. Okay. So then we call the next energy, whatever the amount of energy is taken. Okay, so it will convert into electron. Right? It will get as Na plus 1 electron we will get. So now next is here you can take chlorine molecule, we have to convert into Cl gas. Half mole we are taking, we will get a half mole. So therefore energy we call it as bond dissociation enthalpy. Dissociation energy by 2, because we are taking half mole, so therefore dE by 2 we will take. Then next is, so it will accept the electron. So whatever the electron is being given here, that electron is being accepted by this. So that electron affinity we call, or electron gain enthalpy we call. Okay, electron gain enthalpy or electron affinity we will take. Okay, we will write like this to avoid the confusion. Electron affinity. So therefore, it is going to accept 1 electron and it will be your what? So Cl minus it will turn. Okay, gaseous ion. Now these two will combine to form the ionic solid. Okay, so now here what we call it as what? Lattice enthalpy, amount of energy liberated when 1 mole of gaseous cation and anion combine to form the 1 mole of ionic crystal solid. Okay, whatever the energy is liberated, that we call it as U. So now total enthalpy of formation, how we can calculate? You write here. Delta H of formation is equal to, so what you have to take? Sublimation energy plus ionization enthalpy plus half of dissociation energy plus electron gain enthalpy, okay, plus U, that is lattice enthalpy. Okay, now among these terms, any one of the term if it is unknown, then we can calculate other, from all other data we can calculate that particular energy. So that is what is. So here we are supposed to know the lattice energy. So therefore lattice energy is equal to delta HF minus sublimation energy plus ionization energy plus half dissociation energy plus electron affinity or electron gain enthalpy. So this is how lattice enthalpy can be calculated by using Born Haber cycle. Okay, so this is all about lattice enthalpy and its determination by using Born Haber cycle. We will do problems on this in upcoming videos. Now suppose here we have taken sodium, instead of that magnesium, if it is there, formation of magnesium chloride if we have taken, then here we have to take 1 mole of chlorine gas because it is divalent magnesium, so therefore it will give 2 electrons, and its ionization enthalpy will be plus sum of ionization enthalpy 1 and ionization enthalpy 2, so that you should make note of. So therefore ionization and lattice energy, if you want to calculate, in that case what it turns out to be, delta HF is equal to sublimation energy, ionization enthalpy plus, instead of half dE it will be complete dissociation energy because we need 1 mole of chlorine gas we have to take. So therefore and next electron gain enthalpy also we are going to. Okay, so that is how we are going to determine lattice enthalpy of a ionic crystal indirectly, okay, when it is not possible to determine experimentally. I hope you have understood the concepts what it has been discussed in this particular video. Thank you for watching. Okay. For more videos, subscribe our channel.